Hello, 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 hello. Going to work with you on the solution of the coupled oscillator. Before I start working on it, I'd like you to take a look at my new shirt, present from my wife. She gave it to me yesterday. It's made in Kenya, Africa. The company is Tsuri, and they have wonderful African designs. I'm going to buy a dress for my wife with a different design, but from the same company. I think it's terrific. You may remember that I often, during lectures and during videos, wear this bracelet. That's also from Kenya. It's one of my favorite bracelets. I bought it more than 40 years ago in Amsterdam. So I thought I'd wear it in combination with my new shirt. Remember when I posted the problem that I said if you have two oscillators which are coupled, there are always two resonance frequencies. One whereby the two are in phase and one whereby the two are out of phase. A resonance frequency always means that the frequencies for both objects are the same and that they come to a halt at the same time. If they're in phase, they both go to the right at the same time and to the left at the same time. Then there is another resonance frequency where they also come to a halt at the same time, but if one goes to the right, the other goes to the left. And I want to demonstrate that using a double pendulum. If you watch my lecture 6, I think it's number 6 of 803, you will see there how I derive the resonance frequencies for a double pendulum and even for a triple pendulum. And how I then demonstrate the modes. 2 modes for the double pendulum and 3 modes for the triple pendulum. I want to show you now the 2 modes with an improvised double pendulum. So I have that double pendulum here. The upper mass is an apple and the lower one is a cup with a design by Mondrian. I will try to first excite the lowest resonance mode, whereby they are in phase. This is it. You see they have the same frequency and they come to a halt at the same moment in time. This is easy to excite, this frequency. The higher frequency is harder to excite. But this is it. You see it? They have the same frequency. They come at the same moment to a halt. But when the upper one goes to the right, the lower one goes to the left. Okay, so you've seen both modes. So let's now go to the board. Get a little closer. This will do. Okay. So here we see the 2 pendulums, not the 2 pendulums, the 2 oscillators, the spring system, mass M, and the pendulum with mass M2. This is the frequency in radians per second of the pendulum alone, and this is the frequency of the spring system alone. Let's now make a free body diagram of this object and of that object. So let's start with the pendulum. The pendulum is here. There are only two forces on the pendulum. T, that is the tension in the string, and that is gravity. I have decomposed the tension in two directions. Those are the green marks. The vertical one and the horizontal one. Since the angles are very small, the cosine of the angle is very close to 1. That means that T is therefore approximately the same as M2G. This component in the horizontal direction, which is the one that we have to work with, is T sine theta. And since T is very close to M2G, it's approximately M2G sine theta. The sine of this angle, which is the same as the angle in radians for small angles, is this distance divided by the length. And this distance is x2 minus x1. Because remember, this object is at location x2 and this object is at location x1. And so, since this object is attached here, this is x2 minus x1. Let's now go to this one, which is the spring. There are four forces acting on the spring. The spring force, gravity, and the tension. Because this string is pulling down on this object with the same force as this, of course. The tension is the same everywhere in the string because the string is close to massless. There must be a normal force upwards because the object is not moving in the vertical direction. The normal force upwards must be the sum of m1g and of this component of t. And that is t cosine theta. So the force down is t cosine theta plus m2g. Is t cosine theta, which is approximately m2g, and we have to add to that m1g. And you see this is m1g plus the t cosine theta. So now we are going to write down the equations of motion for each system. Let's start with M2. So M2, x2 double dot, which is the second derivative of x2, that is the acceleration of this object. That one, and we're dealing only now with horizontal forces, is only this force. And that force is m2g sine theta. There it is. And sine theta is x2 minus x1 divided by L. So it is minus m2 g over L, x2 minus x1. So that's number 2. Now we go to number 1. We're only dealing with the horizontal components that matter. So we're only dealing with this one, and we're dealing with this one. This one has a minus sign, it's minus k1x. And this one, t sine theta, remember t was m2g. You see that here. And the sine theta is x2 minus x1 divided by L. And so you see that here. Now m1 equals m2. That was a given. If not, then the situation becomes rather complicated. And so we can divide m out everywhere. There's an m here, m here, m here, there's an m here, there's an m here. And here we divide by m. K over m is the square of the frequency of the spring. Remember, omega of the spring is the square root of K over m. And so we're going to rearrange things a little bit, and I'm sure you can do that on your own. F2 is gone here. I move this to the other side, so it becomes a plus. And so I get a G over L, which is omega p squared, times x2. And then we get omega p squared times x1. One has a plus sign, but it flips over, and the other has a minus sign. So this is straightforward high school algebra, which evolved immediately from this equation. I will leave you alone with this one. Again, you divide out m, and then you make use of the fact that omega spring squared is K over m, and that omega p squared is G over L. So you get this equation. So this I would call the equation of motion for object 2, and this is the equation of motion for object 1. Now, to find the resonance frequencies, this is a standard approach. You substitute in these equations, x1 is c1 cosine omega t, and x2 is c2 cosine omega t. If you substitute that in there, it means that both objects will have the same frequency omega. They have a different amplitude, but they have the same frequency omega. They come to a halt at the same moment in time. When this cosine function is 0, this is also 0. So these are the necessary conditions to find the resonance frequencies. So I leave you alone with putting this in here, in x1 and x1, and putting this in there and there. And once you have that, clearly C1 over C2 that you get from this equation must be the same as C1 over C2 that you get from this equation. And so you can now write down that C1 over C2 for this equation is the same as C1 over C2 for this equation. Here you see C1 over C2 from this equation. And here you see C1 over C2 from this equation. So look now what we have. We have now an identity between omega, omega p and omega s. If you work this out, again high school algebra, you get an equation in omega to the fourth. Because you see this omega squared times this omega squared becomes omega to the fourth. So here you have omega to the fourth, here you have omega squared, here you have omega squared, and what you do now, you replace omega squared by x. It has nothing to do with the x that we had earlier in the position. It's just a symbol x. So you're going to get, this becomes x squared then. So you're going to get an equation which is a times x squared plus bx plus c is 0. That's the way I remember it from my high school days, and I'm sure in high school you learned the same. Ax squared plus bx plus c is 0 has in general two solutions. And I still remember those. They are really brainwashed into my system. X is minus b plus or mean the square root of b squared minus 4ac and the whole thing divided by 2a. And so that's what you do here. So you rewrite for omega square an x. And then you solve. So you finally learn what x is. But since x is omega square and you want to know what omega is, you take the square root out of x. And what you find now is that omega, the plus or minus is the consequence of the fact that you get two solutions for ax squared plus bx plus c is 0. The highest frequency has a plus here and the lowest frequency has a minus sign here. Looks rather complicated, doesn't it? But that's what it is. Since you had earlier C1 over C2, if you want to, you can calculate C1 over C2 using the plus here. You'll find then that C1 over C2 is negative. And the reason why it's negative is that 1 and 2 are then out of phase. So it must be negative. If you use the minus sign and you calculate C1 over C2, then you'll find that it is positive because they are in phase. You can now do some consistency checks. Clearly, you cannot do any consistency check by assuming that m is infinity or that m is 0. That's utter nonsense because you have divided by m. So that means you have multiplied by 0. So you cannot do much with m to check for consistencies. But you can make k is 0. If k is 0, then omega of the spring is 0. The square root of k over m is 0. So when you solve this equation for omega 0, for omega s is 0, you only find one solution, of course, because there's only one object oscillating, and that's the pendulum. And so when you do that, you will find that omega is the square root of 2 times omega p. Now you may say, isn't that strange, because only the pendulum is oscillating. Therefore, shouldn't we find that omega is just omega p? And the answer is no. Because if there is no spring, because k is 0, there still is that object on the table that is connected to the spring, which now doesn't exist. So if here is the table, here is M1, here is the string, and here is M2. Since this is frictionless, if this is going to oscillate, then it's going to, this point here in the middle is obviously going to stand still. And this is what's going to happen. This is not possible, of course. They cannot oscillate in this way. There's only one frequency now. There are not two frequencies anymore. And this is that one frequency. And so it really oscillates about this point, and this length is L over 2. Therefore, the frequency of this system is the square root of 2 times omega p. Because L has now half the length. There's another thing that you can do. You can make the length of the pendulum infinitely long. If you do that, then omega p is 0. So you substitute that in here, and then you find that omega, which is of course only one frequency now, is 1 over the square root of 2 times the frequency of the spring. And that is also obvious. Because Here is the object which is attached to the spring, and all the way down, infinitely far away, is an object with the same mass. And that object with the same mass is not oscillating. Omega p is 0. So the two, when the spring is going to act on these two, the spring is driving two masses. And if the spring is driving two masses, then the frequency is 1 over the square root of 2 times the spring acting on one mass. Because it's the square root of k over m. If m doubles, it goes down by a factor of square root of 2. You could do one more thing, which is perhaps a little silly. You can assume that g is infinitely high. So suppose you did this experiment on a neutron star where the gravitational acceleration is immensely high. Then of course omega p is infinitely high, and so you can remove omega s's here because omega p is so much larger than omega s. You can take omega s out. And when you do that, you find that omega is the square root of 2 times omega p. You haven't learned much, because omega p is already infinitely high, and so the square root of 2 times infinitely high is again infinitely high. So this is not a very useful thing. There is one last thing that you may want to consider, and that is, suppose omega s is the same as omega p. You may think that omega minus, that the lowest frequency where they go in unison, in phase, you may think that that's the same frequency as the spring alone or the pendulum alone. But that's not true. It is less than that. I believe it is 0.618 times the frequency of the spring or the frequency of the pendulum, because we made them the same. If you build yourself a double pendulum, like I did, you use 2 apples, you can check that. Make the strings of both the same length, so they have exactly the same frequency alone. And time that frequency. And then hang them together, and again go to the lowest frequency mode. You will see that that frequency is lower than the oscillational frequency of one pendulum alone. And of course, it shouldn't surprise you that if you make here omega spring the same as omega p, that the highest frequency, where they are out of phase with each other, is higher than the frequency of omega p alone and omega s alone. Okay, coupled oscillators, not so intuitive. But I hope that my consistency checks here helped you. It helped me enormously. I really can see that in this case here, the system is going to oscillate like this, and so I can fully appreciate this square root of 2. And if I hadn't found this square root of 2, I have known that this was wrong. And in the case that I make L equals infinitely long, I can really see that the spring is now acting on 2 masses, which will always stay vertically above each other. And therefore I must now find one frequency which is 1 over the square root of 2 times omega s. If I don't find that, this is wrong. So consistency checks are always very useful. Have a nice day, take care, and try to be friends with me. Okay? All right. So now the numerical answers. So here you see the results which we have just derived, and here is the information that you should plug in there. It's totally trivial, of course, to do that, but it is the best way for me to check whether you did it right or wrong. That's the only reason why I gave you these numbers. So omega plus, that is the highest normal mode frequency, is 4.712 radians per second, and that makes the period 1.333 seconds. The lowest normal mode frequency is 1.342 radians per second, and that makes the period 4.682 seconds. And so, these numbers, for me, are worth their weight in gold. I can tell within 3 seconds whether your answer is right or wrong. Thanks for your support, and thanks for putting these numerical values in. Take care.